Now for part 2 of the notes over reflection and refraction. Change in the speed of light as it passes from one medium to another, or variations in the temperatures and densities of the same medium, cause refraction. Due to the refraction of light, swimming pools appear shallower, a pencil in a glass of water appears bent, the air above a hot stove seems to shimmer, and stars twinkle. The directions of the light's rays change because of refraction. Rays and wave fronts of light refract as they pass from air into water. Wave fronts that enter through the water first are the first to slow down. The refracted rays of light is closer to the normal than it is the incident ray. As a light wave passes from air into water, its speed decreases. So as the ray comes in, oops, I need to hit the button. As this ray comes in, once it hits the water, it slows down, bending towards the normal. So as it slows down, it goes towards the normal. When light rays enter a medium in which the air speed decreases, as when passing from air to water, the rays bend towards the normal. When the light rays enter a medium in which the speed increases, such as from water into air, the rays bend away from the normal. The light paths are reversed for both reflection and refraction. If you can see somebody in a reflection or refractive device, such as a mirror or a prism, then that person can see you by looking through the device also. The laser beam bends towards the normal when it enters the water and away from the normal when it leaves. So you see that here, as it goes into the water, it goes towards the normal, and here, where it comes out of the water, it bends away from the normal. The apparent depth of the glass block is less than the real depth. The fish appears to be nearer than it actually is. The full glass mug appears to hold more root beer than it actually does. These effects are due to the refraction of light whenever it crosses a boundary between air and another transparent material. What causes the refraction of light? A mirage is caused by the refraction of light in Earth's atmosphere. The speed of light in air is only 0.03% less than the speed of light, but in some situations the atmospheric refraction is quite noticeable. A distorted image called a mirage is caused by a refraction of light in Earth's atmosphere. A layer of very hot air is in contact with the ground on very hot days. Light travels faster through it than through the cooler air above it. The speeding up of the part of the waves nearest the ground produces a gradual bending of the light rays. That means the light is refracted. So what happens is when you see this, as it travels faster, you'll get a bend, and it will look like there is a tree down below. Wave fronts of light travel faster in the hot air near the ground, therefore bending the light, making it appear different. A motorist experiences a similar situation when driving along a hot road that appears to be wet ahead. The sky appears to be reflected from the wet surface, but in fact, light from the sky is being refracted through a layer of hot air. A mirage is not a trick of the mind. A mirage is formed by real light and can be photographed. See here in the picture, I'm sure we've seen this as we've walked down, but what happens is the air right there at the surface is very hot, and you're refracting that light, and it's causing it to look like it's wet. When you watch the sunset, you see the sun for several minutes after it has really sunk below the horizon. Since the density of the atmosphere changes gradually, refracted rays bend gradually to produce a curved path. The same thing occurs at sunrise. So our days are about 5 minutes longer because of atmospheric refraction. When the sun is near the horizon, the rays from the lower edge bend more than the rays from the upper edge. This produces a shortening of the vertical diameter and makes the sun look elliptical instead of round. Atmospheric refraction produces pumpkin sun. If the speed of light were the same for various temperatures and densities of air, would there still be images? No, there would be no refraction if light traveled at the same speed in air or of different temperatures and densities. What causes the appearance of a mirage? Since different frequencies of light travel at different speeds in transparent materials, they will refract differently and bend at different angles. The average speed of light is less than the speed of light in a transparent material. How much less depends on the medium and the frequency of the light. Light at frequencies closer to the natural frequency of the electron, oscillators in a medium travel more slowly in the medium. The natural frequency of most transparent materials is in the ultraviolet part of the spectrum. Visible light or higher frequencies travel more slowly than light in lower frequencies. Different frequencies of light travel at different speeds in the transparent material, so they bend at different angles. The separation of light into colors arranged accordingly in the frequency is called dispersion. So a prism will basically disperse into its colors, its natural frequencies. Dispersion through a prism occurs because different frequencies of light travel at different speeds. As our white light travels in, the prism splits it up into blue and red and all the other colors that come from it. What causes the dispersion of light? In order for you to see a rainbow, the sun must be shining in one part of the sky, and the water droplets in a cloud or in a falling rain must be in the opposite part of the sky. A rainbow is an illustration of dispersion. Water droplets in a cloud or in a falling rain must be in the opposite part of the sky as the sun. All rainbows would be completely round if the ground were not in the way. The rainbow is seen in a part of the sky opposite the sun and is centered on the line extending from the sun to the observer. As the ray of light enters a spheric raindrop near its top surface, some of the light is refracted. The light is dispersed into its spectral colors. Violet is bent the most and red the least. At the opposite part of the drop, rays are partly reflected back into the water. Some rays are refracted into the air. This second refraction is similar to that of a prism. The refraction at the second surface increases the dispersion product produced at the first surface. Dispersion of sunlight by a water droplet produces a rainbow. So as the sunlight comes in, it will come in and disperse back out into its colors. Each drop disperses a full spectrum of color. An observer sees only a single color from any one drop. Fly observing several drops, the arcs of each color form the familiar rainbow shape. As the sunlight comes in, you see you got red through violet. At a particular angle, you sweep out the portion of a cone with your eye at the apex. The raindrops that disperse light to you lie at the far edge of each cone. The thicker the region of the water drop, the thicker the conical edge you look through, and the more vivid the rainbow will be. Only raindrops along the dashed arc disperse red light to observe at a 42-degree angle. For your cone of vision that intersects the raindrops creating your rainbow is different from that of a person next to you. Everybody sees his or her own personal rainbow, so when you move, your rainbow moves with you. This means you can never approach the side of a rainbow or see it end on. You can't get to its end. Basically, it's always going to look like a circle to you. Often a larger secondary bow with colors reversed can be seen arching at a greater angle around the primary bow. The secondary bow is formed by similar circumstances and is a result of a double reflection within the raindrops. Most of the light is refracted out the back of the water drop during the extra reflection, so the secondary bow is much dimmer. Light from droplets inside the rainbow from a bright disk with the colored rainbow at its edge. The sky appears darker outside the rainbow because there is no light exiting raindrops at the way that produces the main rainbow. So the light is not getting back here, so that's why it seems darker. If light traveled at the same speed in raindrops as it does in air, would we still have rainbows? No, there is no change in speed, there is no refraction. If there is no refraction, there is no dispersion of light and hence no rainbow. Point to a wall with your arm, extend to approximately a 42-degree angle to the normal of the wall. Rotate your arm in a full circle while keeping the same 42-degree angle. What shape does your arm describe? What shape on the wall does your finger sweep out? Your arm describes a cone and your fingers sweep out a circle. Likewise with rainbows. What other conditions are necessary for seeing a rainbow? Total internal reflection occurs when the angle of incident is larger than the critical angle. Fill a bathtub with water and shine a submerged waterproof flashlight straight up and then slowly tip it. The intensity of the emerging beam diminishes as more light is reflected from the water surface to the bottom of the tub. At a certain angle, the beam no longer emerges into the air. The critical angle is the angle of incident at which the light is reflected at an angle of 90 degrees with respect to the normal. The intensity of the emerging beam reduces to 0. Beyond the critical angle, 48 degrees from the normal in water, the beam cannot enter the air, it is only reflected. The beam is experiencing total internal reflection, which is the complete reflection of light back into its original medium. Total internal reflection occurs when the angle of incident is larger than the critical angle. This is how fiber optics work. A through D, light emitted in the water at angles below the critical angle is partly reflected and partly reflected at the surface. So you see A through D, it keeps getting, the angle gets greater and greater, but it's still reflecting and refracting. At the critical angle, the emerging beam skims the surface. So what it does is it goes up at the critical angle, and then the beam just skims the surface now. Right there. Past the critical angle, once we get past that point, there is total internal reflection, making it bounce through. The critical angle for glass is about 43 degrees, depending on the type of glass. This means that within the glass, rays of light that are more than 43 degrees from the normal to a surface will be totally internally reflected. Total internal reflection is, as the name implies, total, 100%. Mirrors reflect only about 90 to 95% of incident light, so prisms are used instead of mirrors in many optical instruments. Prisms are more efficient at reflecting light than mirrors because of the total internal reflection. The critical angle for a diamond is 24.6 degrees, smaller than any other common substance. This small critical angle means that the light inside a diamond is more likely to be totally internally reflected than to escape. All light rays more than 24.6 degrees from the normal to a surface in a diamond are kept inside the total internal reflection. In a cut diamond, the light that enters at one facet is usually totally internally reflected several times without any loss of intensity. It then exits from another facet in another direction. A small critical angle plus high refraction produces wide dispersion in a wide variety of brilliant colors. The brilliance of diamonds is a result of the total internal reflection. You'll see all these different colors reflecting out of a diamond because of the total internal reflection. Optical fibers, sometimes called light pipes, are transparent fibers that pipe light from one place to another. They do this by a series of total internal reflections. Optic fibers are useful for getting light to inaccessible places. Mechanics and machinists use them to look at the interiors of engines, and physicians use them to look inside a patient's body. Light that shines down some of the fibers illuminate the scene and is reflected back along the others. Optic fibers are important in communications, replacing bulky, expensive copper cables to carry telephone messages. More information can be carried in the high frequencies of visible light than in the lower frequencies of electric current. What causes total internal reflection? That's the end of part 2.